One of the most important types of reactions in chemistry, and one of the best known, is going to be known as either the neutralization reaction or the acid-base reaction. The two names are completely interchangeable. And the second name is really descriptive because it really highlights for us what we're going to be doing. We're going to be mixing an H+, because it's an acid, with an OH- because it's a base. And if you have H+ plus OH-, you're going to get water. So every acid-base reaction we're going to talk about is going to have the net ionic expression shown here. We're going to have other things that are present as spectator ions. Something had to be paired up with your H+ so that it was charge neutral when it was sitting around in a beaker by itself, right? Maybe it was HCl. Same with the hydroxide, but you had to have something associated with it, maybe a sodium. So you could have hydrochloric acid and sodium hydroxide. You mix them together, you're going to get water, and the two spectator ions are still going to be around. You'd have your sodium and your chloride ion that I just brought up, so you'd be making sodium chloride, table salt. That's going to be one case for these reactions, but this is going to be the prototypical neutralization reaction. H+ plus OH- yields water. Now, once you've written your net ionic equation like we have up above, we can decide what products we have. So we have the water. Now we can go ahead and do our total ionic equation. So if we were told that we were doing the reaction for acetic acid and sodium hydroxide, what we would do is we'd say, well, let's use our nomenclature. My polyatomic ions, acetic acid, that tells me it's going to be high H+ associated with the acetate ion. We'll go ahead and write our acetate ion, NH+. We'll have sodium hydroxide, so we'll write our sodium and our hydroxide. Now we know it's got to form water, so that's not really a question mark. If it's a neutralization reaction, it's got to be water. So we'll make sure that it's balanced, and at the moment it is. 1 H+, 1 OH- give me 1 water. Then I look at what else I've got. I can go ahead and put my liquid phase right there, because water dissolved in water wouldn't be aqueous water. It's water, liquid water. So we just make sure it's liquid, not aqueous. We look at this other stuff and we say, right, I have sodium and I have acetate, so my other salt should be the sodium acetate. I still have the two ions sitting loose in the total ionic equation. Okay, and I ran out of space there a little bit, but you can see what I'm doing there. Then I can work it back upward and then write it as my products. And in my molecular equation, I go ahead and I associate these two and give it the aqueous state of matter. So we can work it backward to get the other two. You can see here's my total ionic equation once I've got it all written out. My acetate, my H+, my sodium ion, and my hydroxide ion. And I'm getting my water. I still have my acetate, and I still have my sodium ion. And my molecular version, we go ahead and we write it like this. Often, you'll see it written as NaCH3COO. And that's one of the proper ways to write it. But another thing that people will do sometimes is they'll just snap on the cation wherever the H+ used to be to communicate that we went from having it be the acid form into the sodium salt form. So you will see that there's a couple of times where, despite being so rigorous on our notation, we aren't very rigorous, but it's for a reason. It's that we're communicating where exactly this ion is snapping onto the structure. And that's the idea for it. Now, since we know our solubility, we can also go ahead and put our states of matter. We look at acetate ion and sodium ion. We say sodium ion is always soluble, and its molecules are always soluble. Acetate ion was usually soluble, and certainly soluble with sodium, and so this would be an aqueous state of matter for its phase.